Yeah. It's just a little bit.
Just print it in parallel. So just open 32 windows and print it in each of them, but only 1/32. That'll print 32 times faster. You don't need to make it thread safe. You just need to not care if it's thread safe. So, those of you who are inexplicably in class today, what up? I kind of assumed people would keep coming to class until the end of the semester, but I am updating the favorite student rankings accordingly for all of you here today. So, this will show up on letters of recommendation. I'm teaching pretty much my favorite concept in the universe today, graphs. So I don't know what everyone else's problem is. And I'm teaching also my second favorite thing in the universe, which is also 6 characters, Amtrak, and also trains. Right?
Wow, I hate it. You hate Amtrak? It takes so long, and it always gets canceled.
My door is open.
Last time I took an Amtrak, it did get canceled. Yeah.
Okay. Yeah, it sounds like a skill issue. Have you tried
Amtrak I forgive them. It allows me to get home. Yeah.
Oh, so that's
yeah,
you
bro,
then.
you're biting that feeds you right now.
Okay. So right, what are we doing today?
Graphs.
Yes. So I'm gonna teach you about graphs. And I'm gonna teach you about my third favorite kind of graph, the directed acyclic graph. Because it's after directed and it is after tree. Trees go crazy.
That's true. These are.
And binary trees, oh, that's my favorite thing. It's like a non-binary binary. Okay. And then there's also hash and Merkle trees, and I'm not really sure about that. So I actually didn't give it to you for an assignment. I gave you a sheet for an assignment. The heap T assignment is like partially posted. I don't have the API for it done yet. Because I was trying really hard to get a generative AI to do this assignment, and it doesn't seem like it can. But maybe you all are more patient with the I don't know what to refer to generative AI as, the chorus of idiots, right? Like because you weight it based on how popular things are, and if it's popular, it's wrong, right? Let's name an example of something that's popular and wrong. Ooh, my mind went to the United States. Okay. Anyways, so we'll have heaps of fun after this. What is heap? Yeah. Yeah. How's that not? Okay. Okay. All right. So I'm going to introduce graphs at a high level, and then I'm going to introduce 2 special cases of graphs. And what you'll notice as I add restrictions to graphs, they're going to start to look more and more like things that are very, very easy to work with in computers. And at various points in time, you might think, hey, that looks like a cloud technology, or hey, that looks like a machine learning technology. And probably when you think that, you are correct, right? Graphs are ubiquitous. In fact, a lot of people mistakenly think they breathe air, but actually we can envision molecules as a graph where protons and neutrons and electrons are nodes, and then there's edges between them. So really, you think that's air you're breathing, it's actually graph theory. Okay. So we're gonna just begin by putting the term n-ary trees. That n, unless you have whatever is wrong with Jimmy, is binary, right? For some reason, Jimmy's doing trenary. Yes, that is true. That's not a joke that I made up for this class. I walked into class and that was happening. A tree is a type of graph. Now we haven't defined what graphs are yet. So we have a pointer to graphs, which we're going to deal with later. Okay, oh look, it's the next bullet point. A graph is a pair. Now I haven't defined pairs yet, so we'll deal with that in a minute. It is a pair of 2 sets, usually. The first set is the set of nodes, vertices, or vertexes. I used to come out swinging in favor of vertices, which is, of course, a regular plural of an English language noun. I've since softened my position on the importance of maintaining a regularity, and I think saying vertexes is probably the way we should be going. We should just iron out all of the inconsistencies in the English language. And there's a lot of them, so we should really get going. So I have a set of nodes, or vertices, or vertexes, and I also have a set of edges. The edges are, this says pairs of nodes, but they don't always have to be pairs of nodes. Sometimes they can be sets of nodes of cardinality 2, which I do not think of as the same thing as a pair. Sometimes they are ordered pairs, so it matters which one of them comes first. Yes.
But
Yes.
is this slide saying a graph is a pair of node edges, like there's one of each, or two pairs of nodes or vertices? Not two, one pair of nodes and a set of edges or a pair of edges,
It is a pair of a set of nodes and a set of edges.
pair,
Pair of sets.
one.
And the sets have different types. Okay. There are many ways to understand graphs, and they're all trivial. We're going to use a running example today. For some reason, I started running. You all know this. It's completely changed my personality. I'm extremely Sigma grind set pilled now. I do cardio for fun. That's not true. It's not fun. I do cardio instead of doing things for fun. There. Okay. So we're going to use the running example of Amtrak, which every single person in this classroom without exception loves. Okay? Yeah. Right? Right? So, okay. Do I want to do this? Okay, so imagine you're in Russia in between 1905 and 1917, right? Just imagine, right? And imagine your name rhymes with Vladimir Lenin, right? And you're talking to your mates, right? Who are something that rhymes with Kevolutionary Romunists, right? And you're trying to explain some advanced concepts to them. One of the concepts you might be trying to explain to your mates is the difference between the state and the government. Why does that matter? Because in 1905, there was, I think, it was called the White Revolution, which was when the Democrats, can I get some loud boos for the Democrats? I didn't know my audience, right? The Democrats took control of Russia and probably did something that is technically against the law to the Tsar's family. I don't know. Anyways, and so the Democrats took control of the government, but some of the peasants who are quasi-working class people, they're people that do agrarian tasks, right? They noticed their quality of life didn't really change, even though supposedly this was the end of feudalism, right? And so someone had to explain to them, okay, the government has changed. We are no longer under a czarist monarchy. We are now under a democracy, I guess. I don't know. I don't know what the whites thought they were, right? But the state hasn't changed. And what was the state? The state is what our friend Vladimir called the special bodies of armed men, which includes things like the Cossacks and the armed forces, right? So the armed forces were still enforcing the traditional order of land ownership by private individuals, right? And so, if your name's Vladimir, you have to explain to the peasants and the working class why their conditions haven't changed, even though the government has changed. And the reason is because the government has changed, but the state has not changed. The state is the armed forces that are still serving historical interests, regardless of whether the Tsar is in power or not. Amtrak is part of the government, and it is not part of the state, because Amtrak does not oppress you. It is just something that is managed publicly, right? And it is different in this way from, for example, the United States Armed Forces. It is similar in this way to food stamps. And then there are often things that are not part of the government that are part of the state. And the example I always give is the Proud Boys, right? Which they seem to keep doing things that are very productive for maintaining the current state of affairs, even though they're not seeming to be funded by taxpayer dollars. And they probably are funded by taxpayer dollars, and that's the last I'm going to say about that. Okay, so we're going to talk about Amtrak, which is part of the government and not part of the state. I did not mean to bring up Lenin. I just don't have any impulse control. This is Amtrak. This is also Also, fun fact, I did a little bit of web development here, right? This has a border radius on it. That's how I got this to look so nice when it's embedded, right? And it's animated. I don't know if you saw those little destinations pop up. Oh, look at this. Okay. All right, let's get me out of here. Okay. Did you also notice there's an Amtrak emoji? Right? It's definitely just for Amtrak. I'm pretty much 100% sure it's just for Amtrak. It's an Amtrak train. So that runs on standard gauge rails. Yeah, it's like a lot of people get confused because they don't think it's the Amtrak emoji, but it is. It's actually impossible for me to tell lies. Inside of me are two wolves. They both tell the truth and always contradict. Okay. And you can derive anything you want from a contradiction, such as that a graph is an ordered pair. Now, I'm sure we all know what ordered pairs are, so I'm only going to spend a few slides defining them rigorously. That is two things in fixed order. Oh, we've got a problem here because I only assume ZF set theory, right? And ZF set theory doesn't have ordered pairs in it, right? So I'm going to have to build ordered pair. Now, we can think of an ordered pair as a sequence of length 2. And that's a little thing I like to call cheating, right? Anyways, what is one problem with this? Well, that means a graph is not a set. For example, if we look at the 0th index of the mathematicians, is this mathematical object here, that's a sequence, right? No, we don't know. We don't care. Does anyone care about anything? I hope not too much, right? Because it's going to wither after the. Never mind. Cut me off. Stop talking to me. Okay. This is not allowed. This is banned. This is against the law. And why is that? A lot of people think it's because the set object is not subscriptable. That's not true. It's actually because they're different types of brackets. Okay. There's no real way of knowing. I wonder what this link is to. Oh, wait, no, I can't play that. Oh, stop. Okay, we're safe. Get me out. Okay. Google, don't ban me. Okay. So, some of you probably love pears. For example, for me, it's my second favorite fruit to be a component of a non-alcoholic and therefore any ages and family-friendly apple cider, right? And you can just slam some pears in there, the same as apples, because actually, I think pears and apples are the same thing in some like cosmological sense, right? Any biologists? Any taxonomists?
They are.
Yep, just like tomatoes. Okay, and so I made a number plane, right? Because you can't keep all of your planes at your airports. Some of them you have to embed in your slideshows, right? Okay. So here's a number plane, and we can put an ordered pair on the number plane. And why does it matter it's ordered? Well, if we take the ordered pair 0.5, 1.5, I'm going to follow the social convention that I learned in middle school that you run before you rise. Does that sound right? Any middle school graduates? I have to cross the street before I go up the friends at my stairs house. What if I'm a magnetic levitation friend? Okay, and so anyways, if we did the 1.5 and then the 0.5, it would be here. So it matters that this is ordered because the locations differ, right? Okay. Well, I mean, we shouldn't just assume that we have ordered pairs, right? We should construct them rigorously. So I'm going to do that. And listen carefully. This doesn't matter at all, but I think it's interesting. We're going to take an ordered pair, which is going to be a set of cardinality 2. And I know what you're thinking. You're thinking, oh, Calvin, you can't just put A and B in the set because sets aren't ordered. Not to worry, I have a plan. One of the elements of the set of cardinality 2, which we'll refer to as the outer set, is a set of cardinality 1. So we're going to have a set that contains a set of cardinality 2 that contains a set of cardinality 1, and also contains a set of cardinality 2. What are these two things? Well, I'm going to take what I consider to be the first element of the ordered pair, and I'm going to put it in both of these sets. And then I'm going to include both of these sets in the outer set. So I'll have the set A and the set AB, and I'll take the set, so I'll have the set of A and the set of AB as my sets, okay? That means when I take the set union between these, I will get the first element, and when I take the set difference between the two of these, I will get the second element. And using this technique, I can construct ordered pairs, linked lists, for example, and in fact, you can construct the entire natural numbers out of sets using this technique, right? Because of course I can put something in here with 3 elements, right? No problem. Okay. You all looked like you didn't believe me, and definitely weren't just zoning out because this is uninteresting to you. So this is what this looks like. I'm going to make some variables. We love strings, don't we, folks? Shoestring fries are one of my favorite styles of fries, right? Yeah, right. Okay, cool. This is a disordered pair, right? So we can think of this pair as, for example, being the pair of the government and the state between 1905 and 1917, because there's no order, right? We can construct an ordered pair, which is the, I mean, I hate to say the glorious revolution of 1917, right? But, I mean, I don't hate to say it that much. And we can take an ordered pair where we can put the state, or perhaps the government, doesn't really matter which one's first. And then we put both elements in the second one. And so this is not allowed because you can't do this in Python. Why is that? Unhashable type set? I don't know. So we can emulate it. And this is why Python's a bad language. A, B. Wow, typing is hard. And then we imagine the disordered pair is AB. So, anyways, this is why you can't teach graph theory in Python. But what we can do is, I think I can still take the set intersection of that, right? So, can initialize a set. S dot intersect S0 or S0 in ordered pair. And I might have to cast that to a set. Is that allowed? Do I mean, oh, I have to type out intersection? That's emotionally exhausting. Okay. This doesn't seem to work. I don't know how set theory works. Okay. Oh yeah, so what I should initialize it to be the union. How do I just take the intersection of all of the elements of a list? I don't know how to do that, because you have to initialize it to something. You can do it to the rest of the list. Yeah, but how do I do that in a list comp? Because, and I can't take the first element, right, because I'm pretending it's a list. So I have to arbitrarily select one. Yeah. I don't know that there's a way to do that. Okay. Anyways, this doesn't work in Python, because Python's bad. Okay. Here's my formal definition. An ordered pair is a set of 2 elements, a set containing the head element of the pair and a set containing both elements of the pair. I refer to them as head and tail. I define it in this manner. I don't know that we like defining things this way, but this is how I have decided to define it. Okay. The head element is the element that is in the intersection of the pair, which we say for all y pairs, element of the set of pairs acts as an element of y. And I denote this head. Why do I denote this head? I'm used to calling this head from linked lists. Tail is the sole element of the union that is not an element in the intersection. It's also the set difference. When you take set difference, does order matter? Okay. If none of you know, I don't know. So I got around this problem of ordering by taking the union set minus the intersection. So for all pairs in the set of pairs, x, or yes, for all sets in the set of pairs, x is an element of one of them and is not an element of the other. Okay? This is how we construct head and tail. Now you can make linked lists out of sets, okay? So now we've rigorously defined ordered pair using nothing but sets, and we're good to go. I think we all had fun doing this. So the graph is an ordered pair of two elements. It is the set V of vertices, and it is the set E of edges. I often refer to vertices as nodes, but in all cases, I have always seen graphs specified as G equals VE. So I'm going to preserve that here, and I'm going to use simple parens to denote an ordered pair, but we can imagine at all points in time that that is just shorthand for the set theoretic definition of ordered pair. Okay? So we all know what graphs are now, right? They are not line charts. Okay. So we all love Amtrak universally. Absolutely no one has anything negative to say about Amtrak in this classroom, other than the fact that the state is trying to defund Amtrak because Amtrak is part of the government, right? And that's not our fault. Well, it is our fault because we're not sufficiently well organized as the working class, right? But it's not separately our fault. Okay. So we're going to take V, which is the vertices, vertexes, or nodes, and we're going to think of them as stations or stops or cities. I don't know how you all think of the Amtrak stop across the way. I don't know if you think of that as the Salem stop or like some street stop or whatever, right? I usually think of Amtrak as connecting cities, right? So you can think of a connection between Portland and Seattle, or you can think of a connection between King Street Station in Seattle and Central Station in Portland. That's okay. I don't care what you do. And I don't know the name of the station in Salem, so if one of you knows, I'll try and update my terminology. I think of E, the edges, as the connections, and I think of them as atomic connections. So I think of this as soon as the train stops, I do not perceive there as being an edge continuing this. So I'm only connected to adjacent stations. This is very important because there's actually not a Portland to Salem edge. They stop in both directions in a place called Oregon City. Has anyone ever been to Oregon City? I don't think it's real. I've never met anyone who's been there. And like I know people that have taken the train between Salem and Portland, and none of them have ever seen or reported on the existence of Oregon City. So I think this is what we like to call on the internet a mass formation psychosis, right? Okay. Unlike Vancouver, Washington, which we all know is the version of Washington that is inherited from the superclass Vancouver, BC, right? So this is an instance of the class of Vancouver, right? There are two such instances. And we're all familiar with this because Portland is an instance of the class Portland, Maine. And that's why there's very good lobster in the city of Portland, okay? So we think of Amtrak as an ordered pair and also part of the government, right? But not the state. And we do note the two elements as stations and trains. Anyone love trains? Anyone a train kid in here? Yeah. Does anyone like to go choo-choo? I love going choo-choo. I choose to ride on Amtrak. Okay. So Amtrak is the pair of stations and trains. Okay. Easy. Formal definition of Amtrak. Take that, government. Okay. So let's look at the nodes, vertices, or this is script V, right? That's LaTeX V. I'm going to consider the special case of the Amtrak cascades. Why is that? Because the entire graph of Amtrak is complicated, and I didn't want to write it all down. I happen to have most of the stops on the Amtrak cascade memorized because I am short on hobbies. So here they are. We got Albany. Can I hear it for Professor Kitata Smalley? Okay, that was okay. You all should work on that. Can I hear it for who lives in Portland? Can I hear it for Professor Daniel Barrero? Yeah, right. Okay. I don't think anything's else on here. Do you want to cheer for Vancouver Wa? Okay. Can I hear it? Yeah, woo! Yeah, great coffee shop there called Terrain. Check them out. Right. Okay. Anyone want to cheer for Jeff Bezos? Good job. Okay, all right. Now, some people love complexity, and I do too, but I'm assuming you don't, and I didn't ask you your opinion, I just made an assumption about it. And I'm assuming you only care about the Portland to Seattle 6X daily trains, which fund the entire route. The Amtrak Cascades is cash flow positive. It is actually a revenue generating mass transit service. Those do exist. The people that don't like mass transit don't want you to know that, but I'm telling you. So I'm on your side. You can trust me. These are the stops on the PDX to Seattle 6X daily. There's a place that I guess really exists called Centralia. Olympia exists, but Lacey doesn't. That one's not real. And also Kelso and Longview. That's actually two places. That's why they're separated here with a bracket, right? That's not division, right? This is not the ratio of Kelso to Longview. And I should specify these are this is integer division. So that's Olympia divided by Lacey, and we throw out the remainder, right? I think I'm funny. I don't care what you all think. Okay. E is the set of edges. Also sometimes called lengths. Pretty much always call these hear these called edges. I'm used to hearing both vertexes and nodes all the time for graphs. I think I've only heard edges. Is there a term other than edges that any of you use ever? No? Okay.
Yeah, they're
Arcs?
arcs sometimes,
Yeah.
but like only if edges is taken by something else and you need a separate.
Oh, because you might have like an edge of a polynomial and you're still doing connection.
Yeah, we would flip graphs in water. We had edges and we had a graph where each node of the graph is a polygon and those polygons had edges, and so we couldn't use.
So you called them arcs?
Yeah.
Interesting. I would have called them ordered pairs of nodes. Okay. The edges are pairs of vertices, ordered or not. Yeah, we don't know. Okay. Oh, we're introducing why it matters if they're ordered. Oh, that's so exciting because I was really wondering why we introduced ordered pairs earlier. Okay, so there's a thing called an undirected graph. What's an example of an undirected graph? Amtrak. It connects every station in both directions. Okay, and then we also have an example of a directed graph, a graph with direction. Wow, that's like the negation of me because I am directionless, right? But an individual train, in fact, must progress in one direction as far as I know. I'm not a physicist, but I believe most trains can only move in one direction at a time. So I think like the Cascades 502 only runs south to north or something. Maybe it runs north to south. I don't know. So these edges are ordered pairs, right? What's another example of a directed graph? Well, perhaps pointers are edges that are directed. Yes. Is everyone seeing the connections here?
Yeah.
Yes. Am I hearing the sounds of light bulbs coming on? Because that's what it sounds like to me. There's also some faint wheezing coming from this cabinet. So maybe that's what's going on. Okay. We love directionality. Shout out directionality. The internet I think of as something that is directed in the sense it is very easy to get stuff off of servers and very hard to get things onto servers. Pointers I think of as directed. It is very easy to find the value at a memory location. It is borderline impossible to find out where all of the pointers to some memory location are. This is an open problem in memory safety. And we can't sort of double asterisk something and go backwards. So we have to use this other operation here where we like get the location of a point. I don't know, it's sketchy. So I think of pointers very strongly as being directed. I think of linked lists as being directed. I think of binary search trees as being directed, right? Okay, let's order our route north to south, right? Up in the north, we've got Seattle, and down in the south, we have Portland. There's nothing south of Portland, so if you mistakenly think there's cities south of Portland, you're wrong. Actually, time-space proceeds atomically from Portland to Tijuana, Mexico, right? There's actually no remaining cities in the United States in between Portland and Tijuana. So what does this mean? Some of these pairs are edges and some of them are not. It's pretty easy to tell. In this case, if they're adjacent. So Seattle Tukwila is an edge, and Seattle Olympia is not an edge. And we like things to be edgy, right? Is being edgy still cool? No? Okay. So there are 8 stations, which means there's 7 edges, right? 7 pairs out of 8, right? And here are the edges. I currently have them ordered. I don't know how I feel about that. Really, edges should be a set of ordered pairs, which means these shouldn't be in any order. But I'm going to use the tuple, and that's supposed to say probably notation. So I'm going to use tuples with parens. You can also use set notation in the case of undirected. I think this shouldn't be in an order, but I don't know what order it shouldn't not be in, right? Here's one way to view a graph, and this is often the way I think in graphs now. This is JSON-like. So I have a graph, which is an ordered pair. It's kind of ordered. We got something called V, which is the vertexes, right? This ain't Texas, but you can hold them, right? Lay your cards down, 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 down. Okay. And oh, it's not an ordered pair. So how do we solve that? We place V again in the second set, and then we also place E in the second set. And E is a set of pairs, right? All this stuff is disordered, right? This is like Russia between 1905 and 1917, right? That's a long time ago. Okay. Ooh, it's time for an exercise. Who loves exercise? Yeah, that's what I thought. It's good for your heart, and it's also good for your mind. And it's also good for the exercise and health science department at Willamette University. So some of you are probably familiar with the world's greatest city, Chicago. Some of the Bears, Cubs, Sox, and Bulls, right? Jordan played there. I attended my undergraduate institution there. It is located relatively geographically close to Jacob's hometown of the derivative middling regional city, St. Louis, right? Is that correct? Yeah. And everyone loves St. Louis, but they really love Chicago, right?
Yeah.
Yes. Okay. So we love Chicago. And if there's one place we love as much as Chicago, it's Milwaukee, right? Milwaukee, Wisconsin, right? Okay. There's also a Milwaukee that is inside of Portland, but it's spelled differently. And one of my family members lives there and is trying to leave as quickly as possible. Okay. Let's just read a little bit about the degree to which Chicago high ski slaps, is I believe how this would be described. From the grandeur of Grants Park's Buckingham Fountain to iconic museums and skyscrapers, see for yourself why Chicago was once dubbed Le Prairie in Le Prairie. Engage in retail therapy. Ooh, capitalism mentioned. Ooh, gross. The state, it's leaking in at all times. On the Magnificent Mile, or root for the home team in the friendly confines of the famed Wrigley Field, named after the gum, right? I think? Okay. So we all love Chicago, world's greatest city. As an exercise, construct a graph of the Hiawatha route, named after... I'm not supposed to say Iroquois. I don't know what you say instead of Iroquois. It's the long house people from what the colonizers refer to as upstate New York. Use the JSON-ish notation, or you can use actual, real, live existing JSON. Take a look at the route here. It has relatively few stops on it. Oh, look, the internet works. Oh, I'm gonna allow all of the cookies because I trust Amtrak. Just kidding. I'm gonna reject them all. Okay. So, oh, Chicago, Milwaukee. Notice how they don't show a picture of downtown Milwaukee? That's because downtown Chicago looks like this, right? That's the Chicago River. Okay. Take the route. I used 3-letter codes for everything. And you can write valid JSON if you want to. So, with a partner or individually, depending on how antisocial you are, perform this exercise and construct a graph of the Hiawatha route. Ready, go. You have 7 minutes. Is that not a reasonable number of minutes? No. Okay, there we go. Timer.
Oh,
Yeah. You know, graph art.
Yes. It was really cool.
Yeah, we can.
When I say not very graph.
Stupid.
Yeah.
You want to make discussion with things not attracts this week?
Sure.
Yeah. We should try to make you understand.
Yours might be. I was not.
Or,
Oh, I was. I don't know. I'm also. That means I have to do each tables the right way. Yes. 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 Oh my goodness. So there's a Mexican somewhere.
I'm just now.
That is like.
Yeah, that'll do. Okay. And reading
You have to, let's say you have a loose list, you points to the tail?
Yes.
Okay, then you don't need. So. What you need to do is you need to DL all the nodes and then DLC and then DL the either the head or the tail, depending on where it first. So you can just traverse it for it to hit at each step.
and then free.
I think so. That was giving me some choice.
That's
As long as it frees itself. Okay, we'll leave some slightly. So I'll help with that, Brian.
Oh wait, actually, wait. Okay. I know these guys. We're also just camera. I forget to say stuff.
Also free.
Oh, because I used to.
See. I'm really good. Yeah, that's
Make me this set.
Yeah, from like.
Lots of article on how people use these quotes and you know, so they can go into the office.
Yeah.
I think that's me, yeah. Understood. It's although I live for the magic thought.
I can probably do things. Okay, so how we get the pilot and above.
Good with all those flags. Go.
You're forgetting.
I feel that like.
Oh.
I just.
Now it you where
Oh, that's helpful. Thank you very much.
that's just me and see about information. Although it's information to be able to recreate during these times. So you need to
I see. Which originals that we was the biggest, but then people have to see. Maybe I got all.
You got it.
I got the face. Yeah.
That's a lot. These aren't much of a decision. It's like
This is pretty bad.
yeah. Are you gonna do the depth? Yeah, I think you can do that. It's kind of the.
Interesting.
Why do you tell it's all that?
I mean, that.
That feels like a shader. Like, why not? I use this definition. Charlotte. Oh, yeah, but it means
Which we put some notes. Oh, by oh.
Just use this.
Well, clearly it's like a family something. Okay, I'm leaking less memory.
But.
Yeah, but barely anything is valid.
So that it, is that it replaces the valid levels in your program with input ballots, and then it has its own simulated version of memory, and it keeps track of it. So background isn't basic. Like insert, it's not like interpret, so it replaces valid, it's a valid, it uses that to study your. So it can keep track of all the but. I get a little bit confused, when I get some document errors from that, well. It might be good at the thing wrong, if at the end of the program, you have just things like reference, memory, not reference.
This guy codes,
All I know is that the way of the Rust one, version about excellence, that's the interpreter.
starts out with starts to, but eventually be able to this works. What was talking about these things. If you have like, so we should go through these things. It's kind of crazy. Basically, like starts with the idea of a doorway, it's a portal. And you cut the doorway in half, moving pieces of different places. A portal is from in front of that assumption, but kind of these are those things from each side where. He was first to make a little bit of muscle. It's like a ring between seconds. It's like everything portal rings. And then eventually sort of sense. It was nice.
Who even needs memory? Who even needs help? More leaks?
You're probably gonna get some other.
Certainly. But hey, right now I got. I changed the tester to be more reference and test for even more. Oh, I added flags. Reading that over. Yeah. And then now I can bring it back to the running board. Actually, oh, let's see. Yeah, that's hard.
No, I just thought of something. They don't have a network on our.
Oh god, are you unable to do something that you were expecting to be able to do?
I could theoretically do direct memory access with IO. And some kind of drive with it, IO interrupts to do network transfer. To hold you hardware acceleration. And hardware acceleration in my case means breaking Rust and not ternary assembly. So I really want things to be hardware accelerated. But I think this is good for now.
Okay, like, but now surely the rest of it should be triple, right? That's right.
But it's like,
Okay. I'll try. I have a video and I book there was a German race. I know.
That's beautiful, isn't it? Just coming.
Yes. One of the journalists exposed him to negatively by being just what books the podcast and stress.
Fuck you. Yeah, sorry.
You're wrong. Blue. Fine. Yeah, I know.
They're great. Sorry. That's so great. You're right.
Running, one meetings, I had one.
That's where you're really right.
It's great for you. And then if-
I think I've never seen.
I was wondering about the- Shucks. But if you had to advise.
White. No, I just checked. Here's a complex number. It's white. Yeah, that shouldn't have been allowed. All right, you all know what graphs are? Congrats. Everyone give yourself a big old pat on the back. Okay. They're not real, but they're actual. This is a directed gay cyclic graph. What's that? Don't worry, I got you. Okay, all right. All right, I need everyone to lock in. I know I've asked you to lock in a lot of times, but we're in the home stretch, right? I was counting how many classes we... announcement. No in-person class next Tuesday. I have a guest speaker who's in Boston. Boston, right? Which means we're zooming. We're zooming from 3 to 4. This person's going to tell us some things, I don't know what. Been trying to get this guest speaker here for approximately 100 million years. Because 100 million years is logarithmically the exact same length as a semester, cosmologically speaking, right? Because of log orders, right? So somehow I'll have to like send out an email or something, or it'll be a Zoom link.
I was saying, it's same
3 to 4. So we're cutting 10 minutes off the beginning and 20 minutes off the end.
What did you say that?
1 week from today. I will definitely remember to tell everyone this and not drive down here and then find out that we're doing Zoom class. 100% I will not forget about this. Can I get a brave volunteer to make a note in Discord right now?
Yeah.
Okay, thank you. Do it. Okay. Cycles. My favorite one is, of course, I love biology. I've mentioned that. My favorite one's the Calvin cycle, which is something to do with cellular respiration. It's been a long time since I've been biological, so I don't remember it that well. We're going to take a set of pairs of edges, we're going to take a set of pairs of vertices. I'm going to think of the edges in a graph as one of my favorite things, a homogeneous binary relationship. We all love homogeneous binary relation. Oh, it just says relation. Okay, never mind. No relationships here. The ship of relation has sank. Okay? So it is homogeneous. What does homogeneous mean? This means we have a binary relation from one set to itself. There's only one set in play here. And this is the set of vertices, right? So we're relating vertices to vertices. Oh, that's edges. Okay. And it is binary. That means there are two things in the relationship. So we're mapping one vertex to another vertex. And I think of relations as sets of pairs. You can think of them as other things. That's how I think of them, right? So addition, for example, is addition a good example? No, negation is a good example. Negation is a homogeneous binary relationship over the integers, and I guess also the reals, and also the q's, the raddies. Okay. Now I know that you all know and love homogeneous binary relations, right? We all know that. We knew that before we came in here today. But we also know and love transitive closures, right? And I'm going to find a transitive closure over a homogeneous binary relationship. And by golly, at the end of this term, if you say you don't know discrete mathematics, do not say that in earshot of me, okay? This is the most discrete mathematics has ever been. That's not true. That would be combinatorics. Okay, sorry. I got a little too hypey there. Okay. Okay. And I think we all know and love Cartesian products, right? This is how we multiply sets together. A relation R over a set S is a set of pairs of elements of S. How do I think of this? It is a subset of the set of all pairs of elements, right? And the Cartesian product, what? Hey, you love Cartesian products, right? Is that not what it is? It's an extremely useful way to think about it if you're me, because this is how I think about it. How do you think about it? Okay, no, I need an alternative. I want to have viewpoint diversity. Please. You don't think of it as a subset of the Cartesian product? It's a sparse matrix. Oh, do you not like the plain text? Think on this and get back to me. If like, I'm fine with people not liking things because I don't like things. Now I know your two favorite languages are HTML5 and LaTeX, right? So I've specified the Cartesian product here in both of these, just so you can know what it looks like. I got super duper into writing all of my mathematical expressions in HTML until I tried to write a division. And then I went crawling back to LaTeX and apologized for ever saying mean things about LaTeX. So anyways, I do think aesthetically this looks better, and I also think it's more portable, because I think this uses math fonts, which is provided through a CDN, and that CDN is provided by Cloudflare. And Cloudflare was responsible for providing DDoS protection to Stormfront, which is part of the state and not part of the government. Anyways, moving on. Who loves traffic lights? Beep, beep. I love a traffic light. Yeah, okay. And what traffic light colors do we have? We've got red, green, and rello. What?
Are you 6-letter old?
No, it's just green, yellow, red. That's fine. Okay. No, I underscore terminate them. I pad with underscores when I do this in fixed width. Okay. So we've got our colors. We've got green, yellow, red, right? The Cartesian product of the set of colors is green, yellow, green, red, yellow. Moving on, right? Yeah, I think we can all agree it's time to move on, right? We've been here long enough. Okay, so what is a relation over this? Well, we take the Cartesian product and we take some subset. I'm going to take what I'm going to call traffic light L. So L is a subset of the Cartesian product, and which is C cross C, right? This all makes sense. We know what's going on, right? Okay. So we're going to construct the traffic light relation. We're, by the way, going to use the traffic light relation to prove safety, liveness, and other security properties next week. So pay attention for that reason, if not for any other. My understanding of the requirements of the traffic light relation are that you may not have red without the previous being yellow, which means that if the second element of a pair that is an edge, this is an ordered pair, is red, then it must be the case that the prior pair is yellow, right? Okay. And then we also have all colors must appear in both positions. What does this mean? This means that the colors can continue to sequence or cycle or whatever you want, right? Oh, wait, did I say cycle? By golly, I wonder if we're going to rigorously define cycles, right? Okay, not to worry. Okay, so the light relation is green goes to yellow goes to red goes to green. I think this is the only satisfying relation. Apparently, there's like lights in Washington that have other states, but Washington's not a real place. It's named after a settler colonizer. Can I get some booze for settler colonialism? I don't know. I don't live in Washington. I bet no one in here has ever lived in Washington. That's why no one cheered for Vancouver, Washington when I brought it up earlier. It's okay. Vancouver, Washington is actually part of Oregon. Right? It's weird. Yeah, right. Really? Kaiser doesn't? I love that. Shout out Kaiser. They're an incremental improvement compared to private health insurance. I mean, I don't know. I don't know how you're planning on solving the health insurance problem. Short of calling up your buddy Latimer. Okay. There's a variety of ways to express this. I don't care how you express it. I do love infix notation. Oh no, it was a matrix the whole time. Oh, right. Yeah, I'm sorry. So we've got our initial color in this case. No, that's not our initial color. These are our initial colors because green progresses to yellow, yellow progresses to red, and red progresses to green. Okay. Do you not love this? Anyways, this means you can store the all of the edges in 9 bits, by the way. So very low information density. Okay. This is a rainbow. You may have seen these before. These are associated with there was a film. Wasn't like Russell Crowe Noah recently? Yeah, this thing. Rainbows were invented in 2014 in the fantasy adventure film Noah. So you're probably familiar with those. They're also now associated with, I think, homosexuality. So that's just 2 good things, right? Okay. I'm going to order colors by wavelength, which is something physicists know about, and it's inversely correlated with energy, I think. Oh, yeah, optics. Yeah, physics, optics. Help. Okay. If you see someone that knows what wavelength is, thank them for knowing that, right? Because I don't. Okay. So we're actually going to create another relation now, and we're going to call this the rainbow relation. And are we going to denote it R? No, because R is taken for relation. We're going to use the B, because I didn't know what other letter to use. So we're going to make rainbow relation B. And we note in our rainbow, as we can all see here, that red is above yellow, and yellow is above green. Is that true? Red is above yellow, yellow is above green. Yes, okay. Green is above nothing. Green is an imaginary color that doesn't actually exist, right? So it has nothing in its column, right? It's not better than anyone. It's just like us. We're all exactly as good as each other, right? So we're going to take rainbow relation B, which is also a binary relation. We take a subset of the Cartesian product, and it's going to have red, yellow, and yellow, green, okay? And okay, hear me out, right? So red is perhaps more, I guess it's probably less energetic than Y. How do you know that? Okay, you are all very smart and I'm very proud of you, okay? I'm going to continue to progress through my stupid era up here in front of all of you, and you can just enjoy the carnage, okay? All right. So we note that whatever red is in relation to Y, it is also that in relation to G. And that's transitivity. Yeah, 7 is greater than 6, and it's also greater than 5, right? We love 7, 6, and 5. Why is 6 afraid of 7? Yep, okay. So this is how I define transitivity. If AB and BC are in R, then AC is in R. If red and yellow are both, if red is above yellow on the rainbow and yellow is above green on the rainbow, then red is above green on the rainbow. That's transitivity, okay? This is true. This is good, okay? So we can take the closure, and that would just be populating. Well, I guess we have to decide if things are more than themselves, right? I think of closures much more interesting in the Amtrak case because I can connect stations to other stations. So if I can connect to Oregon City from Portland or Salem, then those things are connected to each other. Okay? Now, in order to create transitive relations from boring, uninteresting, homogeneous binary relations, boo, totally overhyped, right? We take our boring, homogeneous binary relation and we transitively close it. A closure is an operation over sets, specifically sets of pairs. And we're going to take the set of pairs and we're going to increase the size of the set of pairs until we achieve the minimal size set that has the property of transitivity. Okay? How are we going to do that? Well, we're going to denote the transitive closure of something as, I just called it R+. This seemed common in literature. If you have seen another way to express transitive relations in one of your other classes, let me know, and I'll update the terminology. We note that the transitive closure is a non-strict superset of the homogeneous binary relation. Why is that? Well, every edge that is allowed in the homogeneous binary relation must be in the transitive closure, because we have to have at least those things. And we're just going to add in some other stuff, okay? I missed the right arrow. That's why I had to stop talking there. I didn't lose interest. Okay. So how do we solve this problem? For all pairs, in this case of colors, each one of them is in both the homogeneous binary relationship and the transitive closure thereof. Okay? And I've expressed this mathematically here with respect to the Cartesian product of the sets of colors, right? Because, oh no. That's supposed to say B. No, that's binary relation. Okay, all right, we're fine. Keep going. Okay. Is everyone having a good time? Okay, that's good. Okay, so we take the transitive closure, R, and we're just going to restrict it to have a few properties. We're going to say that this thing must have the property of transitivity, which means we have already rigorously defined transitivity. If A, B, B, C, then A, C, right? Okay. Okay, I did this as a for all. This is how we get Amtrak connections. And so if we have Seattle Amtrak Tacoma and Seattle Amtrak Tukwila, then we must have Tukwila Amtrak Tacoma. Okay? I don't know if this is the best way to express the Amtrak relation, but I did it. Sorry. I'm not sorry. Why am I sorry? Okay. If in rainbow relation B we find R is higher than in the rainbow than Y and Y is higher than G, we say RY and YG, then we must additionally add RG. AB, then BC, then AC. Easy. B+. That's the grade I'm getting in this class. You all get an A. Okay. R+, the transitive closure, is the smallest possible relation. Why is that? The Cartesian product is transitive. You might not care about that. But this means there are multiple possible transitive supersets of many homogeneous binary relations. And we have to take the smallest one, because otherwise we're not really taking a transitive closure over some relation. Really, we're just calculating the Cartesian product, and we already know how to calculate the Cartesian product. We do exhaustive pairing across our constituent sets. Okay, so what is the transitive closure? It is a homogeneous binary relationship, which is transitive, which is a superset of some relation, and which is the minimal sized relation that satisfies the first two requirements. Easy. Okay. By the way, those binary relations are graph edges. Oh, and those edges can be pointers. Okay, let's keep going. Okay. So we all love cycles, right? Anyone love cyclocross? Did it slap? You seem uninterested. Okay, we'll keep going. So I'm going to use transitive closure to define cycles, because why not? I actually just wanted to introduce transitive closure for no reason. That was completely unrelated. That was self-dealing, is what they call that. So I'm going to take a graph G. I'm going to transitively close E, the edges. The set of edges is a homogeneous binary relation. So I'm going to take E+, which is the grade my non-favorite students are going to get in this class. But I only have favorite students, so you're all safe. Okay. G, graph G, contains a cycle, or has the property of being cyclic. Containing a cycle and having the property of being cyclic are logically equivalent, right? If the transitive closure of the edges contains an edge from a node to itself. Okay? How do you find that? Cyclic G equals VE if there exists little v in the vertexes such that VV is an element of the transitive closure. What does this mean? It means you can get from an edge to itself. Sometimes this is good, because oftentimes when I'm taking Amtrak, I want to go somewhere and come back. That's a cycle. Sometimes this is bad. I don't know when it's bad. When are cycles bad? When you have negative feedback loops, probably, right? Yeah, shipping. Yes, we don't want to ship my sick bomber jacket I got from Team Liquid through. Yeah, look it up. Okay, all right. We define cycles to be non-trivial because edges may contain self loops. That's boring. We don't care about that. And the reason we don't care about that is because even if I connect from Portland to Portland on Amtrak, I usually do so without taking a train, which means there's not an edge. Okay. Okay. There are other graph terms. I'm not going to define them. This is a DAG, a rigorously defined directed. It means the edges are ordered pairs. A rigorously defined acyclic. It means there are no self-edges in the transitive closure of the edges. And a rigorously defined graph. A graph is an ordered pair of a set of vertexes and a set of edges. Right? Any questions? Speak now or forever hold your peace. Does anyone know if it's P-E-A-C-E or P-I-E-C-E?
I think it's PE.
Hold your P. Like,
Like,
do not urinate?
Yeah.
so speak now or don't.
What we
Or
want.
you really have to go to the bathroom, but you only have one opportunity.
You have one shot.
If you're about to
One opportunity.
guy,
I wonder if I can do. What is the one shot, one opportunity song? Yeah. We're losing ourselves. Yeah. It's the spaghetti song.
That's okay.
It's the spaghetti song. I was happier before I remembered that I'm recording this. Okay. Cascades 503 goes from north to south. I guess it connects Seattle to Portland, probably. It's a DAG. No cycles. Amtrak Cascades is a DAG because you can go in both directions on it. Who loves taking Amtrak to Vancouver? British Columbia. Look, I didn't name the city after another state on the same train line, right? I think do people call it the Couve? Okay, because I was calling it the Couve like to make fun of it, and then I found out people do that unironically. That's so based. That's so cool. Okay. All right. Actually, south, was it southwestern or southeastern? The southern region of Washington that is part of Oregon, according to Kaiser. Sounds rad. Okay. Color wavelength is a directed acyclic graph because R more than Y more than G, and R more than G. That's a DAG. Okay. A traffic light is not a directed acyclic graph because Y goes to R goes to G goes to Y. Oh, there's a cycle I can loop forever. In a way, this is like Sisyphus, right? Pushing a boulder to the top of a hill, right? Every day. And then what happens? I think Zeus throws the boulder back down to the bottom of the hill. I don't know for sure. I've heard some people suggest that Zeus isn't real, but then who throws the boulder down the hill at the end of every day, right? That doesn't make sense, right? Have any of you heard of friendship? Right? So friendship, a lot of people know this, was invented in the Ridley Scott film, Thelma and Louise, right? So we have Thelma and Louise. They're friends. This is an undirected edge. So that means Thelma and Louise are not a DAG, right? And this means Facebook is not a DAG. Because people are allowed to be friends with each other, technically. Now, it is true that now Facebook is a DAG, but when it first came out, it wasn't. The new computer science major that I got mind controlled into offering next year, even though it's a ton of work for me and also for you, so I don't know why we did this. This is directed acyclic graph. No cycles. Why is there no cycles? Because no class can have a prerequisite of one of its postrequisites, right? So all of these arrows are directed down. I was able to order this north to south, if you were. Is this a link somewhere? Oh, hey, it is. Okay. Register for classes. I am declaring advising bankruptcy, which means I'm getting back to you on a best effort basis. If we get too close to the registration window, I'll just blanket approve everyone to sign up for classes and we'll figure it out in the ad drop period. Okay, yes.
Would it be correct to say that rock, paper, scissors
Yes. And yes, with respect to the monogenous, ring, 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 monogenous. Yes, with respect to the beat relation,
Yes.
which is named after the Michael Jackson song "Beat It." Okay. Who loves trees? And I am talking about weed. Okay, a tree is a DAG where every node has at most one incoming edge. There exist undirected trees, but not in this class. This computer science class. We only have directed edges, shout out pointers, right? A graph is a tree if, for every vertex, any edge which contains that vertex in the second position, or the final position, or the destination position, the cardinality of that set is 1. So there is at most one incoming edge. Really? Where? Oh, yeah, but I'm like memeing on how it's spelled. That's a stylistic typo. They're not all stylistic, but some of them are. I have some... Oh, so... Okay, correct. I was trying to decide how to spell leaf. Yeah, did you see it? I got complete... Where is it?
Yeah, you just went past it.
Yeah, right. Okay. Because I also could have said vertexes here, right? Ooh, why did you say that? now I will. Okay. Get me out. So an example of a tree is a decision tree. Wait, do I have... Where's the Mocha decision tree? No. No, okay. So I walk into archive coffee plus bar, right? And I announce I'm straight edge because I'm not breaking edge, right? Okay, so that plus bar, that's not for me, right? That's for other people. We all love minor threat, right? And I say, can I get an espresso? Oh, that's my first decision, right? Then I make my second decision, single origin, right? Because my favorite Spice Girl is Posh Spice, which means you must drink single origin espressos, right? That's an example of a decision tree. And if you pick a non-single origin, then you have to pick decaf or not, right? So there you go. Decision tree, boom, easy. Everyone understands making decisions. And as you know, all decisions are binary, okay? Here's another decision tree. I don't know what this is of. It looked pretty confusing to me, but this is the example. I think river systems are trees, and I think that this is probably not something that necessarily must happen, but at extremely high probability. When rivers go downstream, they don't divert into two streams indefinitely. They always reconverge. So this is the Columbia River system. And we'll notice we have whatever this river is that's coming in here, and like the William Amet, right? It goes into Columbia here. I don't know if we can still see the mill stream on here, right? But every tributary at most goes into one either other tributary or the principal river itself. So here we go, naturally occurring tree, right? I hear there's other forms of trees in nature, but I've never heard of them other than river systems, okay? And there's also the tree data structure. What's everyone's favorite data structure? And you have to say not hash tables. Okay, what's everyone's favorite data structure? Correct. Okay. Wow, you just hate the Hadoop distributed file system? Oh, well, it's not my fault you hate operating systems. If you're trying to store data, you really only need one way to get there. So in a computer, it is commonly more efficient to use a tree. If you're trying to assure the integrity of data with hashing, you really only need to hash something once. So it's common to use a tree. These are the two examples we're going to consider, okay? Da-da-da-da! It's a data structure. Who loves data structures and algorithms? That's what I thought. That's the wrong tick mark. See that? Okay. By convention, given a directed edge, vertex v is denoted as the parent, and vertex v prime is denoted as the child. I think of it this way. I learned data structures in C89? Hell yeah. Can I get a hell yeah for C89? There was not a lot of hell yeahs there. Okay. And so one way to do this is, oh, you got some data. Then you have some children. We all love children, right? They're innocent and blameless before God until they become adults, right? And then we also have the struct tree, struct star. What is this? This is an array of other trees. These are the directed edges to other trees, right? Okay. Nothing about this is preventing you from having a DAG or, in fact, any other kind of graph. Just by convention, we are going to accept this as a way to implement a tree, okay? It is quite common to use binary trees because computers like things to either be 0, 1, and as we were discussing before class, they also have these like high impedance electrical engineering states that we don't think about because they're confusing. So commonly, we use a binary tree where there's two children. The children are named right and left. Left is spelled L-E-F-T and right is spelled R-I-T-E because they both have to be the same number of characters, right? So we're all familiar with that. By the way, you can implement a list T using this data structure. You just don't use one of the two sides. So this is a serialization of a linked list. Does that make sense? Does it make sense that a linked list is a tree? I need you all to agree that makes sense. Okay. I need to hear heads rattling in skulls while you shake them, right? Maybe that's only my head that rattles. I suspect I'm losing brain mass over time due to my lifestyle, but I can't actually verify it because I don't know how to measure your brain, right? I'm worried that's non-independent from some other factors. That measures volume, does it not? Into my skull. What if my brain's getting denser? A what trend? Radon? I measure how much radon's coming out of my brain?
No, it's
Okay, so I compute a radon transform to get the density of my brain, and then I perform displacement. Did you suggest irradiating my brain? Okay. I'm going to start wearing a tinfoil hat to class. Okay. I'm going to make an exceedingly strong claim that I don't know if this is true. In 100 level CS classes, students often implement a binary search tree. Righto. These trees tend to store lower values on the lesser or left side. Yeah? Yeah. I just realized I taught some of you data structures, and now I'm very nervous. Okay. Yeah, I know. I'm not allowed to teach data structures anymore because I taught it without using classes. That probably shouldn't be allowed. BST sort is pretty similar to quicksort. So if you throw things in a binary search tree, you're essentially pivoting on a series of elements that's logically equivalent to quicksort. Do we all know what quicksort is? Some of you seem to know it more than others, and that's okay. In this class, we'll instead do a Merkle tree or a hash tree. Why do we? I'm not really into sorting people, right? I only have favorites, which is everyone, right? Sort of a universalist. Me and Pope Francis believe everyone's going to heaven, right? That's why we're both good Catholics. I think they should make me the next Pope. I think that'd be cool. Okay. Merkle trees are unsorted, but they are verified. What's a Merkle tree? We'll figure out next time. In a blockchain, we store the Merkle root of a transaction tree. The Merkle root, the root, is the ancestor of all nodes in the tree. And this verifies the integrity of the entire transaction tree. And I did not write integrity on this slide. I said integrity. Integrity is a technical term that I hope to introduce next week. Okay. This is what a Merkle tree looks like. This is the Wikipedia. I'm going to make my own Merkle trees Thursday. How's this work? We have a series of, these are essentially transactions. They're called data blocks here. That can be a transaction. What do? We hash every transaction. Then what do? We hash the pair of hashes. And we hash pairs of hashes until we get a single hash. And this is the most hashed of all browns. What can brown do for you? I'm going to introduce some tree terms because I think I'm going to say them next time, okay? Welcome to vocabulary class. Do you all remember elementary school? I don't. I blocked it out completely. I'm still better at doing multiplication by 7 than other numbers because when I learned multiplication in 3rd grade, we learned multiplication by 7 first. That's a true story. I have a multiplication by 7 accelerator installed in the wetware in my brain. Trees are connected. What does that mean? It means you can get to any node from some given node. That given node to which you can get to all other nodes is the root. So if we take the transitive closure of edges, there's an edge from one node to every other node. Okay? This is the set of paths. I haven't defined path rigorously. Don't worry about it yet. By convention, there is no requirement that when I give you a graph, there is a way to get from any vertex to any other vertex over edges in that graph. With trees, we often restrict things to make sure that there's always some path from the root to that. And that's mostly a nicety. The root is the node which has a path to every other node. It is the ancestor of all nodes. So a lot of people don't know this. Ancestors were invented by Miyazaki in 2023 when Elden Ring came out, and they had 2 different kinds of guardian spirits, and they needed to give one a second name. So that's where the concept of ancestry comes from. So thank you From Software for inventing ancestors. Okay. Often in computings, we treat a descriptor or a pointer to the root as a descriptor or a pointer to the graph. So if I hold the root, then I have a way to get to every element of the graph. If I take the first element of a linked list and that element contains a pointer to the second element, then I have a way to get to every element. A Bitcoin block contains the Merkle root of the transaction tree, so that means from a Bitcoin block you can get to every single transaction, and you can verify the integrity all the way down to the transactions, okay? Leafs cannot be pluralized. I tried. I did it on this slide and I failed. In a tree, not every node has outgoing edges. Why? Because nodes have at most one incoming edge. And that means there has to be some nodes that don't have outgoing edges, because you're gonna run out of edges, right? Namely, the root's not gonna have an incoming edge, right? Okay. So we're gonna refer to nodes without edges, without outgoing edges, as leafas. Okay? Is there a convention? People really do it this way? They don't.
Yeah.
It's not the same word that you pluralize this way. Both vertices and leaves are irregular? No wonder people don't understand graph theory. Teach the rest of the semester in mouses?
You'd think.
No, I don't think ever. Okay, here's a diagram. 2 is the root. 2, 10, 5, 11, and 4 are leaves. Okay? This is how we use the term parent and child. A parent has an outgoing edge to a child. Parent-child is just relative to a pair. So this is the incoming and outgoing element of the homogeneous binary relationship. Both trees and nodes within trees, or vertexes within trees, have a height and a depth. For a tree, the height and the depth is the same thing. It's the length of the longest path. So this has a height of 3, because the root to the furthest leaf is of distance 3, and it has a depth of 3 for the exact same reason. Nodes also have height. The height of a node is what the height of the tree would be if the node were the root. So if we regard 3 as the root of some tree, boom, boom, has a height of 2. Depth is how far something is from the root. 5, 3, 4. That has a depth of 2. Size is what you would expect. It's the number of nodes. Every once in a while, we want to refer to the number of leafs, and I don't know a good way to do that. So if you know that, you have 48 hours to get in touch with me. Today, you learned about graphs, DAGs, and trees. See you on the next day. What? Wait, we have 5 minutes left? Why was I going so fast? Any percent. Wow, I was so stressed out. I definitely miscalculated something. I thought I was already overtime.